So in this lecture, we're going to talk a little bit about addresses and then about keys. So we'll start by just doing maybe a review, maybe some new material on binary formats, and then a little bit on how to create keys, and a little bit on this big fancy phrase, which means making keys from other keys, so hierarchical deterministic key derivation. So when you're representing binary data, there's a few different display formats that you should hopefully be familiar with, both for using things in cryptography in the future and also just for blockchain in general. So we've got hex, which is numbers 0 to 9, A through F. This is the most common, super standard. We've got base 64, which is capital A's, so capital letters, lowercase letters, 0 through 9. And it's also got a plus or a / in there. And also with base 64, you might see equals at the end. They use them for padding. And then this is much more cryptography or blockchain specific. We got base 58, which as far as I'm aware, kind of came into use for the first time with Bitcoin. So this is base 64 without what they consider confusing pairs of characters. So not sure if you can tell which ones those are, but that is a 0 and a capital O. Those are gone. We've got an L and a capital I. Those are gone. And then also the plus and the slash for good measure. So these binary display formats, let's be very clear, that doesn't mean that internally in the computer's memory itself, this is necessarily using these formats. This is a way to have people see what binary data is, or to transfer binary data through human readable strings. So in memory, these all correspond to the same binary. But in a string, or if you're sharing something with someone, that's when you would use these types of formats. Also with hex, oftentimes you will see a 0x at the start, which sort of just represents this following thing is in hex. Sometimes for binary, you see a 0b. It's not super standardized in terms of when you see it and when you don't, but these are the main three formats that you should be familiar with. And so here's an example of the exact same binary underlying and what it looks like in these three different formats. So in hex, it looks like this. This is a representation where every hex character is exactly 4 bits of binary. And so this 9 is for these 4, this F for these 4, and so on. With base 64, every character is exactly 6 bits. So this N is for these 6, the W for these 6, breaking across the byte boundary. And then way over at the end, you actually see this equals. We won't go into exactly when you see them, but the basic reason that it has to be there is this U is actually only for these 4 bytes. Because it's every 6, and binary is typically broken up by 8, sometimes it doesn't divide right at the end. So that's why you'll see the equals. You don't need to know about it or think about it, just be aware sometimes you'll see it. With base 58, this is the output that you see. Base 58 characters are usually about 6 bits. It's surprisingly complicated, so just take it as base 64 without some stuff and don't think too hard about how it encodes and decodes. Shockingly, encoding base 64 to base 58 can actually be an n-squared operation in the worst case. If you're curious about it, you can probably look it up and there's some article written about it, but a little surprising. So now that just a little review on the binary formats, we've got mnemonics and seed creation. So seeds are secrets. So both symmetric and asymmetric cryptography require secrets. And when people talk about a seed, that's what they mean. They mean this is the secret. And they might use it in certain ways, but fundamentally that is the underlying secret piece of information that other people don't know. If you have a seed in cryptography, don't share it. It's not public. It is your secret information. Now, mnemonics are a way that is sometimes used to represent a seed or to represent some random information because they're easier for people to remember. And so what this is they'll use a dictionary of words and give people phrases, usually either 12 or 24 words, just because they're easier to back up and recover than byte arrays. They're also easier to type in correctly because your brain can kind of think about them better than if something was an F or an E. One thing that's important with mnemonics is never, ever, ever should you go create your own mnemonic and then get the seed from that. You should always go randomly create the seed, then get the mnemonic from that. You are bad at making things random. We all are. Computers are really good at it, so trust the computer. And then in terms of a little bit of the implementation of that mnemonic to seed, they'll just use some standard dictionaries to define which words are included to generate a phrase. Substrate uses the dictionary from BIP39. It's just a phrase that you'll see the BIP39 that defines a way to do this mnemonic to seed and back. And so those are just the first 5 words in their dictionary. Now, also, the secret key in asymmetric cryptography might be a specific algebraic construct, like a point on an elliptic curve, not actually just some bytes. So then you need some defined way in order to get from your bytes to your algebraic thing. You won't need to think about this when you're using cryptographic libraries, which is what we're trying to do, but it's just nice to know. So like BIP39 does a bunch of hashing on their seed before they get there. Substrate, we just use the byte array directly. Both are fine as long as the seed is secret. And if the seed's not secret, the hashing doesn't help you. So in terms of portability, different ways to go from mnemonic to seed will not work with each other. You have to make sure that if you're using a different key derivation function, so a different way from going to mnemonic to secret bytes and secret bytes to algebraic thing, that it's the same across different things. So that might be one reason why you can't use the same mnemonic in different wallets, maybe, because they might use different functions to go from that mnemonic to your secret information. So in the rest of this course and in general in blockchain, you'll mostly encounter 3 different types of cryptography. These are really just, these are signature schemes, is what they are. So we've got ED25519, we've got SR25519, which is a variant of ED25519. You'll also hear this one called Schnorr. And then we've got ECDSA. Sometimes you'll hear it called like SecP because that's some of the underlying stuff. But these are the 3 that you'll need to keep in mind. You'll see them both in this unit, and then you'll also just see them throughout this academy. So what is an address? An address is a representation of a public key, and it's potentially with some additional contextual information. So addresses will just follow some address format, and usually, maybe not all the time, but they'll often include a checksum so that a typo can't change one valid address to another one. This checksum will be implemented with a hash function, like we talked about, but it'll only be just a little bit of a hash function because you're not really worried about your public key having malicious input. You're not worried about things like that. You just want to make sure if I change one character from this valid address, like I change this E to a 3, the output is not a valid address. This doesn't decode correctly, and you can't accidentally send it to the wrong place. And just as one example, we'll talk about the SS58 address format, which is the one that's used in Substrate, even though there's nothing that fundamentally ties the 2 together. So it's base 58 encoded. So again, you take the binary and you base 58 encode it, so to get it to a string. And it includes a checksum and also some context information. Why you might use that or want that context information is something that we'll get into throughout the crypto lectures, but also just so that you can't use the same address in multiple places. If someone sends like, I'll send them some money, and who's them? Well, it's that address. You don't want that same thing to be used in some other context. You want to be specific about where it can be used and make sure it can't be misinterpreted. So the specific way this goes is you just base 58 encode, you have your context, and then you concatenate that with your public key and concatenate that with the checksum. So the vertical line is used for concatenation, but it's not super complicated. It's just one particular way that people decided to do this and hopefully make it human readable-ish. So now we'll go into key derivation. So again, the big fancy term, hierarchical deterministic key derivation. all that means is that you're got your root secret, you're doing some stuff to it, you get one key. You do some deterministic stuff to it, and you get to other child keys. Because, and this is the reason that this works, this is secret. And most of the time what these steps look like is a hash function. So maybe you have your master key, and it is your secret key side of the master key. It's not the public key. You hash it, and now you use that to get another key. That's all this is. So it looks very complicated. Sometimes it's made out to be very complicated, and sometimes the specifics can actually be complicated, but the idea hopefully is not too hard. You're just using a secret thing you already have, and then basically like applying some derivation step, which is deterministic, to get to another secret and using that to make another key. I see a hand, but I will get to the hand in another few slides. So key derivation, you can also have two rough forms, hard versus soft derivation. So key derivation in general lets you derive as many as you want child keys from one quote-unquote parent key. There's hard derivation and soft derivation, and they potentially preserve different relationships. So there's also a little bit of a terminology difference between different forms of security discussion versus Bitcoin versus Substrate in terms of how we call these different derivations. So a hard derivation is where you can only go from, you get from your parent private key, so your secret, and you can use that, you can derive your child private. There's no relationship between these public keys whatsoever. You cannot go from your parent public key to the child public key. If you see the child public key, you don't even know it's associated with the parent. It's a hard derivation. A soft key derivation is where you can both go from the parent private key to the child private key, but also you can go from the parent public key to the child public key. So someone, an outside observer, could look in and say, oh, you know, this child public key belongs to this parent public key according to this relationship. The problem with that, and it's not an unusual problem, it's just something to be very aware of, is notice how this arrow is one way. You can only go from parent private to child private. This arrow goes both ways. If you lose your child private key, you also lose your parent private key. So you need to be careful if you're doing that. And so hard derivation requires the secret key and gives you new child secret keys. Usually as an input to this hard derivation, it'll just be some so-called derivation path, which is just some string input to kind of add to the hash function pretty much. Usually you want to use hard derivation over soft derivation unless you have a very compelling reason to use soft derivation. And even if you are using soft derivation, you should do hard paths first and then conclude with soft ones. So in wallets, hard derivation might be used to turn the same root secret into a different thing for each blockchain system that you might want to use. So maybe you have the master key, and then you use a hard derivation on that with the word Polkadot, and you get to the one that you're going to use in that ecosystem. Do the same thing with the word Bitcoin, get to that one. So this is just, again, like with most of this derivation, it's based on convention. There's nothing like cryptographically special about doing it with that string or really about normal hard derivation. It's just changing a secret to a different form. It is all convention-based, but it's useful to know about because, again, it is used. And so, yeah, that's the use of this. So in the interest of time, I'm going to skip this demo and maybe come back if we have time at the end. So soft derivation, now a formal definition, we just can create derived addresses from only the public key, and all of the keys are related. So, you know, again, like I said before, you can go from the child private to the parent private. all of them have to be considered equally important to keep secret. Additionally, soft derivation is not always possible. It depends on the cryptography that you're using, whether or not this is something that can be done. In Substrate, it does work with SR25519, but you won't always find that soft derivation is something that exists. And then, so just again, remembering about how this is derivation off the same root secret. These do generate new addresses. They generate new cryptographic private and public keys, but they use the same root secret. That second sentence is maybe a little bit related to the demo that I didn't do. So, and then in wallets, as a use case, you can use soft derivation to link payments controlled by a single private key without needing to expose the private key to show all the different addresses. So as an example, you might have, oh, here's my private key, and then I'm going to give someone a particular address to pay me at. And then when I receive a payment at that address, I know it's from them because I told them to pay me at the derivation path of my address and then some unique number. So if I tell you to pay me at, the soft derived child key corresponding to 101, that's your invoice number. Once I receive a payment there, I know it's from them. That's potentially one way you might want to use this. I have 5 minutes? All right, perfect. And I think that's the end of the slide. So great timing. This is a short little lecture. I'll take questions. I'll describe the demo without doing it, and then I'll take questions, and then maybe I'll do the demo. Probably not. So the demo is just an example of using a command line tool called subkey. I'll share maybe in the Element Chat announcements, maybe on the Notion page, the instructions to download that if you want it, of using that to generate from the computer randomness, generate a secret and then the corresponding address, and then a demo of doing some hard and soft derivations, and then showing that you can go from the address to derive the same child address. So just quick little demo of a command line tool that may potentially be useful in the rest of the academy, but I will share some information if I don't have time to go over it, which I don't think I will. So I'll take a few questions, and then Aaron has a few things to say before we go to lunch. So I remember there was a question here, like in the middle of the lecture. I don't know if there still is.
Yeah, so I'm curious, like before you were talking about this hard and soft derivation and this hierarchical deterministic key derivation, and I'm curious if children are compromised, can the seed be compromised as well? Is there a difference between the hard and the soft derivation, and does that make each child less secure, or?
Yeah, so if you have hierarchical key derivation, and let's say it follows this path, and let's also pretend that all the lines in the chart are hard derivations, except these three. These three are soft derivations. So if you lose your seed, they're all compromised. If you lose your master key, they're all compromised. If you lose the child key, all compromised. If you lose this key, then this child key is compromised because it was soft derivation, as well as the other siblings of this one, the other children of this soft derivation. However, if you lose this child key, this one's fine, all the rest of them are fine. In general, hard derivations only compromise their children if the secret is leaked. So you can safely make a hard derivation off of this one, get a secret key, and you can share it with the world, and you're not risking anything. You're still fine, and this master key is secure. With a child key, if you make a child key and you share it with the world, the master key is compromised, and then anything that implies is gone too. Hopefully that clears it up a little for you. I remember there was a first part of the question, I think, and I think I covered it, but I can't quite recall.
Okay, so like then it seems like hard derivation is better. Why would we need like soft derivation?
Yeah, so the only reason that you would want to use that soft derivation is because you can go from the parent public key to the child public key without you needing to tell them what the public key is. So if you wanted to receive payments on a different address, or if you wanted to, I'll just use that example still. If you wanted to receive payments on a different address for each customer with a hard derivation, then you would have your parent public key, and you would have to manually tell everyone, hey, this is the address you should pay. They can't do any checking. If you do it with a soft derivation, you can tell them, hey, this is your invoice number. Here's how to figure out the address you need to pay at. But then you can still control the funds here because you have a child private key.